Morning. Today we meet in a different environment due to our government regulations. I decided to stay at home, but anyway we will make our everyday business. So back from Boulder, Colorado, as to the picture to our kitchen. Good morning. Last time we had been discussing electromagnetics, especially magnetic field. We will continue in that. Now we also had a task and we have one successful reply, so that's excellent. And that's why we will continue, and I will have for you some other puzzle for today, but let's wait for that for a few more minutes. So let's start with another topic in electromagnetics. To a certain degree, we are used to electric circuits. They have a source, some load, some connecting wires. That's what an electric circuit is. So for example, it might look like a source providing voltage and connecting wire and a load. So this source has electromotive force and it causes current to flow through the circuit, through the load, back to the source. And this is a concept we are quite well used to. So we understand that increasing the voltage in the source would increase the current and therefore the power consumed in the load. And that increasing resistance of the load would decrease the current and therefore the power in the load as well. Now, we can find something similar in a broad class of magnetic cases, especially called magnetic circuits. Magnetic circuits are somehow similar to electric circuits. If you create an electric circuit, you mostly have some conductors that intentionally conduct current from one pole of the source to the other pole through the load. Now the same case might happen in magnetic circuits, just those conductors would not be made out of copper, but some material that has better properties. By the way, copper is quite bad in that because, as far as you remember, we classify it as slightly diamagnetic. So in fact, replacing free space by copper does not improve the magnetic property. Now, if we have that, we would possibly make something like a conductor out of metal that is mostly available, which is iron. There are special irons that have good magnetic properties. Of those, many irons are enriched by special ingredients. We will talk on that later when we will meet eddy currents. But now, let's say, well, we will take a piece of metal, we will carve it, and finally we will make a loop of that piece of metal. Now, where the source is, so we will have something like, for example, I'm trying to make a loop which is rectangular, but is easier to manufacture. So we would have a loop like this. I'll try to make it 3D. So we have had a stick of rectangular cross section and we bent it to make a closed loop. This is a kind of magnetic circuit. Magnetic field could flow around it, but we have no source in it so far. So how to get there a source? Well, that would be quite easy. We can add several turns of electric conductor, and having that, if we impose some current into the winding, there would be magnetic field created by that current, and that field would mostly flow through that circuit. Now, with magnetic circuits, unfortunately, we mostly do not have very high precision because most of the materials are not very linear. So that's bad and good. That's bad because we can't get very high precision in calculations, at least in linear way, but it's also good. We do not have to bother rather much on the precision of our calculations so that we can make something like the first or zero estimate and it works. So now, how to find out this circuit, how to solve it? First, the important point we would like to find out is the magnetic flux in that magnetic conductor. We should possibly name it in the common way. Normally it is called core. So the magnetic core of the circuit, and we will also be possibly very interested in the question what the inductance of the winding is. Now this is an important question because it will shed some light on the easy and intuitive definition of static inductance, because this definition needs to be carefully read to get good results. Now, okay, so we have this circuit, and there is an important law of nature which is called the Hopkinson law. Well, and that law is quite formulated like the Ohm's law in the integral formulation. So in the Ohm's law you have voltage, total current, and resistance. And for the Hopkinson law we have more or less the same formulation. It states that you have a magnetic voltage, well, in brackets, which is equivalent to a product of magnetic flux and reluctance. If we put it into brackets, let's call it magnetic resistance. Now, reluctance, voltage and flux. There is one important point that causes a lot of troubles. We have units for this. Let's start with the first unit of this voltage, magnetomotoric force. Well, this is a bit tricky. It is caused by current that encircles the core. Now this is ampere as to the unit, and the unit according to law here is ampere. But any electrical engineer should think that there is a second component in determining this magnetic force, magnetomotoric force, and that is the number of turns. You could get the same effect by putting there one turn and 1 kiloampere, or 2 turns and 500 amperes, or 1000 turns and 1 ampere, and vice versa. Which means that the old and somehow forbidden unit is ampere turn. So you should still know that there is an important number, the number of turns. You know, a turn is not a main unit, not an auxiliary unit, it's not a unit in Système International d'Unité. But anyway, it is important to understand that the number of turns with an inductor matters. So this is the first point. The second point, magnetic flux, which is in Weber. And then you have the reluctance, which can now easily be determined. It is quite easy. If you divide the equation by Weber, you will get the reluctance unit. You can do it on your own. And now we have a simple law, and we should possibly somehow describe how to use it, because this is quite important with simple formulas. So what the reluctance is? The reluctance is given you can define it from the Hopkinson's law, but as a matter of calculation you would get it as an integral of 1 over mu S dl, where mu is permeability of the material of the core, S is this cross section, and L is the length, the total length of the circuit, and you integrate to an element of length. Well, this is an integral definition. For most cases, for most simple cases, you would not have mu and cross-section dependent on the length. If you watch this circuit and you omit the corners, you would have a constant cross-section, hopefully the same kind of material, which means that this is a constant, and therefore you can make it a bit simpler, which brings us to a simple equation for a reluctance of a piece of magnetic material with constant cross-section, and this would be now we know that the reluctance would be given as a ratio between the length of this loop, permeability, and cross-section in the denominator. Now this is quite simple. It resembles a simple equation determining a resistance of an electric conductor. Just you would substitute simple resistance and specific conductivity of the material here. So it's quite a simple case. It's quite a similar case to electric circuit. Now if we have this, we will be possibly able to determine the total reluctance of this magnetic core. To be able to do it really, we would have to introduce some dimensions. So let's introduce the dimensions. Let's say that the core, as we told, it has been made of one stick, so the cross section of all those parts is the same, And let's assume that we made a perfect job, and this is the same length as this, and this, and this. So it's symmetric in this X, this, this, and by the way also in this X, cutting into two half slices the whole core. Now if we have this symmetry, in fact we have four parts, four identical parts that form the core all together. And as reluctance behaves like resistance, we could say that those are four reluctances in series. The whole flow flows through 1, 2, 3, and 4 identical parts. So the total reluctance of this core would be 4 times the reluctance of one side of the core. And this side, now let's make the dimensions. So let this be A. Let this be B, the thickness of the core. And now let's put here a dimension which we call C, so that the whole run around makes 4C, and the cross section of one part is A times B. And due to symmetry, it's the same for all the parts here. So now, provided that the core has a permeability of mu, and provided that this permeability is much higher than the permeability of the surrounding media, like air, we would be able to put down the reluctance of the whole magnetic core, and it would be 4C divided by mu AB. So the reluctance is just a short question, is that realistic that mu is much bigger than the permeability of the surrounding media? Well, yes, this is why we fabricate magnetic cores, to have significant impact on the magnetic field. And fortunately we have materials like steel with relative permeability, that is, they can guide magnetic field, let's say 1000 times better than the air. Now there are also special materials, mostly called permalloys and supermalloys, which can get 1, 2, or even 3 orders of magnitude higher in special circumstances. But classically we use steel, special steel compounds to do a good job for magnetic circuits, and 1000 times higher permeability than the air gets us to the assumption that there will be significant part of the magnetic field conducted through the core. But yes, there is some leakage always. Now we have this simple equation, and we can now ask questions about magnetic flux in the core and also about the inductance. Now let's first start with the magnetic flux through the core. So we have the Hopkinson law. We would know the current flowing into the winding, let's call it I. Now we can easily make a product of current and the number of turns N. And if we do that, we will arrive to magnetomotoric force, and then we can easily establish the flux because we already know reluctance. So let's put down the flux. It's magnetomotoric force divided by reluctance, which is phi is I, the current, times the number of turns divided by reluctance, which is 4c divided by mu A. B. Let's make it look a bit smarter so that we will consolidate the fractions, and our result would be I n mu A B over 4c. So this is the value of magnetic flux in the core measured in Webers. But a short remark at this point. For many applications it would be the best way to have as high magnetic flux in the core as possible, or as high magnetic flux density. Unfortunately, most of the materials we can produce, or all the materials, have nonlinear behavior, and at some flux density they stop to behave as magnetics. So what you can really use with steel compounds is up to 1.4 Tesla. So this gets us some information about available magnetic fluxes in the core of certain cross-section. Now again, let's go back. We have the magnetic flux, and you still possibly remember that we have defined inductance, for example, using static definition. And the static definition states that inductance is a ratio between magnetic flux and the current that has caused it. So it's this equation. But we should now examine that carefully. This flux is not this flux. Again, this flux that flows through the inductor is not equivalent to the flux that goes through the core. Now you say, why? Well, let's examine it again. The flux passes through the inductor, but it passes through 1, 2, 3, and finally n turns of the inductor. And in this case, we have to consider the total flux through the inductor, which is n times phi. So there is also an alternative equation that says, okay, it is n phi over I. Now the important point is what phi means here and here. Those are different phis. This is the magnetic flux that flows through the magnetic core. So if you cut the core at any point, you would get this flux through the cross section. While this, so that's this phi, and this phi is the flux that flows through the inductor altogether, and it counts when it passes through each turn of the inductor. So this is a flux through the inductor, and this is the flux through the core. Those are different fluxes and they differ times the number of turns. Having in mind that, we will be able to find out the inductance of our inductor. Well, we know that this is the flux. We know that this phi c is given by this equation. So let's just substitute this for phi c over here, and we will get an equation. So first we will get, for this case, that the self-inductance of the core would be n squared mu a b over 4c. As you can see, current has cancelled out of the equation. And by the way, if you just compare the equation, it also holds that this is a square of the number of turns divided by the magnetic reluctance. Now this is an important result. We could obtain it by just manipulating symbolically with the equations. But this is an important result that says us that once we double the number of turns, we will get 4 times the original inductance. So the inductance depends on the number of turns quadratically. Now we have examined the behavior of magnetic cores. We have formulated Hopkinson's law. We have used it to calculate a simple inductance and flux within the core. And that's a piece of job we have done, and now it seems that a good time for questions. So your questions, please. I will just, okay. Let's get 1 more minute for questions.
Sorry?
Yes?
The magnetic flux with the M is the magnetic flux through the whole core plus the conductors. Or
Well, not plus, times.
what? Sorry?
Well, you have the core, and within the core you have this flux. Well, so I will put there, this is the flux core, okay?
Yeah.
So you have the same flux at any point of the core, any cross section. But now you have n turns, and the flux in the core times the number of turns makes the flux through the inductor, or the flux in the core times the number of turns, because it counts each time it passes through a loop.
Okay, yeah, I understand. Thank you.
We can also talk of that as from the standpoint of the dynamic definition of an inductor. It says that, just the dynamic definition we remember, we have the voltage, which is minus inductance di over dt. So it depends on the time derivative of the current. But now, if you have 1 turn, there is some induced voltage. If you add 1 more turn with the same flux in the core, you have double the voltage. If you add n turns, you have n times the voltage that was in an individual turn. So this is why we have to count it so many times. And this is why, as this inductance is the same inductance like defined in the static definition. We just have different views of the same entity. So then we have to count the flux in the core the times of the turns of the inductor. Is it more clear now?
Yeah, thank you.
Welcome. Are there more questions? Now just this is a very important point because we have simple definitions like this or this, but you should really properly understand what is written in, otherwise you get misleading results. So again, a short repetition, we have studied magnetic cores as an analogy to electric circuits. We have noted that the source function here is current times the number of turns. We have been formulating the law of Hopkinson. Then we used a simple case to calculate reluctance, which is defined integrally but could be in many cases simplified to a simple fraction. Then we have found out the flux in the core. We have multiplied it by the number of turns to get the flux through the inductor, and then we established the inductance. And we found out that the inductance depends quadratically on the number of turns. If you double the number of turns, you double the magnetic flux in the core, and it counts 2 times in the first and second, the doubled part of the inductor, so the total flux in the inductor got 4 times bigger. Now, ladies and gentlemen, it's time for a short break. So hello again. We will now try to discuss another aspect of inductance, which I already have been touching a week ago. As you remember, I have classified inductances into 2 distinct categories, and that there were self-inductances and mutual inductances. And another type of classification was internal and external inductances. To do that, we will first try to think about an inductance of a wire. Now, this inductance of the wire is composed of 2 parts. One of the part is the external inductance that is caused by the magnetic field surrounding the inductor. In fact, that was the inductance we have used to calculate the inductance of a piece of coaxial cable a week ago. But now there was another inductance which could be hidden in the core in the inductor, which is called conductor in the cable. So what if we have a conductor of circular cross section, and this conductor has a current at DC which flows inside, so I will mark it this way. The current flows into the board and then to minus infinity somewhere, and we have the current flowing there, and as this is DC and the material is homogeneous, we would have a constant current density within this cross section. So that current density would be J. Just we can connect it to the total current that flows there. As the flux density is homogeneous, that would be J times the cross section of the wire, and as this wire is a kind of circular and has the radius A, then the cross section would be A squared pi. So we would have the total current I, which is pi A squared J. So this is to learn what is our source function. We have some current, it's distributed absolutely homogeneous over the cross section, so we have the homogeneous flux density. Now we would like to establish the inductance that is caused by this wire. Let's describe the situation even better. Due to the fact that there is some current inside, let's say at the middle of the conductor, we would have a magnetic field that makes circles around it. The field lines would be circular, and you will get those lines in the conductor inside, and this flux will account for some inductance. Now we would be happy to use the same equation as we did, the static definition, but there is a trouble with it. I mean, the definition holds, but we will not be able to use it. I will show you why. If you have the definition telling that the inductance is a ratio between flux and current, well, we might be able to calculate the total flux that flows in the core, but the problem is that each part of the flux is caused by different current. Remember, this equation says you divide the flux by the current that caused it. But remember the Ampere's law. So if you have, for example, this field line, the flux through it is affected only by the portion of current that flows inside. But this field line will be affected by more current. And therefore you cannot use this definition, because if you use that, you would make a mistake and you would not proceed according to that definition. So what remains us is a more complicated way of calculation, which is to use the definition that is energetic. This works, but is a bit more consuming as to our work. But nothing can be done else but to use it. First, I will use, just as an analogy to electrostatic field, I will declare that there is some energy within the magnetic field, which you probably agree with, and this is again 1/2 of the product of field intensity and field density. In the linear case, the energetic density of the magnetic field is 1/2 B times H. Now this is an important quantity that says, okay, there is some energy in the field and it is distributed not homogeneously but depending on the field. And when the field is inhomogeneous, we have proper density at any point. Having this in mind, we would be able to calculate the energy contained in the conductor due to the flux flowing through it. Just we have to establish the value of B and H, and as they are linearly dependent, we will possibly do with one of them. So now let's find out the magnetic intensity inside the conductor with homogeneous flux of current. So what we have to do is to get the correct current that is contained in a field line, a flux density line, for example, at some radius. So let's define, I will magnify this a little bit, and after I finish this calculation I will just use it and get another paper. So the first part of the description, we have the cross section. And there is a current flowing through that with flux density or current density J. Now if we make here a vector r, which is the distance from the center, from the axis of the conductor, then we could say that there is a line at which we can carry out the integration in Ampere's law. So it would hold that, according to this, 2 pi h is equivalent to I. But we have a number of currents on this white sheet today, so I would make it a I with apostrophe. That's the current that flows through the cross section inside a circle with a radius r. Now we should possibly establish the value of this current in respect of the total current flowing through the whole conductor. So first, let's establish the current density as a function of the total current. J would be the total current I, that's the current flowing through the whole conductor, divided by pi a squared, where a is the radius of the conductor. This is A. Now, provided that the field is homogeneous, we know the current density at any point of the cross section, and we can get out the current flowing through any part of the cross section. For this circle, it holds that the cross section of the circle is pi times r squared. So we could formulate the amount of current flowing inside, and that would be pi r squared times j. And again we can go on and say, okay, this is the original current I times pi r squared divided by pi a squared. We can cancel pi, so the current flowing through a sub part of the conductor, a cylindrical inside part with the radius r and the same center as the conductor, so the cross section has, would be I times r squared divided by the radius of the conductor squared. So now we know the current that flows here, and we also can establish the value of the magnetic field intensity H, which would be, now H, H would be I divided by 2 pi r. That's the original formulation from Ampere's law. And now we can substitute the value of I, and we would get I r squared over 2 pi r, and then we can cancel I against r against r squared, and we still miss something, and that something is and we get r over 2 pi a squared, and we have r in the denominator. So now we have established the behavior of the flux or in magnetic strength inside the core. I will just illustrate it on a short graph. If we have the radius, so we have zero magnetic field at the center, then up to the distance called A, up to the radius of the conductor, there is a straight line. Magnetic field intensity is directly proportional to the radius up to the surface of the conductor, and then, as we remember, it falls down inversely proportional to the radius. But this is not matter of our today's business. We are working with the field inside the conductor to establish the value of internal inductance. So we now know that the magnetic field depends this way on the radius. Now I will have to put this paper away, so I need your possible questions to this part. I will only use the results later, and it will be not so easy to return back. Are there any questions? Or is that clear? Okay, so now we will go on to establish the total energy contained inside that conductor. We will use the value of the magnetic field intensity to be able to do that. Oh, this might work. Okay, so again, we have the value of the magnetic field intensity. I will rewrite it. H as a function of radius is equivalent to I, which is the total current through the conductor, R divided by 2 pi A squared. this is the magnetic field intensity. As the media is linear, we can also specify the value of flux density, which would be mu times h. Just good to remember that. And now we know that the energy density is 1/2 of the product B H, which in this case, due to linearity, could be simplified to 1/2 of mu times h square. Now, bearing in mind this, we know our energy density, and we could be able to find out the total energy in some space, in some volume. For example, the whole conductor volume in 1 meter length. So let's make a calculation of the energy that is contained in the conductor of 1 meter length. Again, we would need to integrate through the space. Now let's find out the differential. So if we have a piece of the conductor, and we will try to cover the whole conductor, we could integrate along the length, which makes no sense because it's homogeneous. So if we cut just 1 meter of that length, we will have the work done. But what we have to do is to make the integration around the conductor, which is axially and radially. Now radially, we can derive an element which will be 1 meter long, will be very thin. This is dr, and this is the differential in radius, and of course it would be somehow big in the angle. So this is dr d alpha, 1 meter long, but we touched it last week. Well, if the element is inside, like in the middle, it would be smaller. With the same dr and d alpha, it would be, if it will be closer to the surface, it would be bigger. It would have bigger volume. So the correct element of this size has the volume of 1, that's as to the length of 1 meter, but then it's dr, d alpha, but it's times r. So this is the elementary volume we have got here. And with this element in mind, we could put down the integration to achieve the whole energy content. So we would have the total energy, this big W, the magnetic energy in 1 meter of the wire, and it would be an integral from 0 to r to a, which is the radius of the conductor, an integral of 0 to 2 pi, which integration is done according to the alpha, of the magnetic energy density, small wm, times the element, which is r, okay, interchange d alpha, dr. So this is the integration we should carry out. Fortunately, we have established the value of the magnetic energy density, and what we have to do is only to put it into the equation and then carry out the integration. So that is something that is quite easy, but needs some work. On the other hand, we have been lecturing, I have been lecturing and you have been listening just for 1 hour, which brings us somewhere to the middle of our lecture, today's lecture, and both you and me deserve a time for 5 minutes break. So see you in 5 minutes. Well, hello again. We are here to continue with the calculation. So we would have to put down the integrand and then carry out the integration. So let's return to the magnetic field energy density, which could be obtained through magnetic field intensity, IR over 2 pi a squared. And let's carry it out. Okay, so the integrand would require the integration from 0 to a of 0 to 2 pi, which would be the whole circle, and the integrand would be h squared mu divided by 2, so we would have mu over 2, and then h, which is I r divided by 2 pi a squared, that squared, times r d alpha dr. Now, having this, let's watch the expression a little bit. So we have constant, 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 all that is constant except of r raised to the third power. Okay, so let's do a simplification. Let's put all constants ahead of the integration mark, and we would get mu over 2 times 4, which is 8, pi squared, a raised to the fourth power, and in the denominator we would also get I squared. Let's check that whether we have not forgot anything. 2, that's 8, pi squared a fourth. Okay, now integral 0 to a of the integral 0 to 2 pi of r raised to the third power dr, the alpha, which again is a simple one. First, we can carry out the integration from 0 to 2 pi. As to alpha, this is a constant, so we will get alpha as the primitive function, and this integration results in a multiplication by 2 pi, that's the whole. So again we have 2 pi mu I squared divided by 8 pi squared a raised to the fourth power. And now we can get here the integral of r squared, r raised to the third power, from 0 to a dr, which could be rewritten as r raised to the fourth power divided by 4, and we should give the upper and lower bound, which is 0 and a. For the lower bound we get 0, so the whole result is obtained by substituting a for r into this expression. So let's make it and cancel some terms. So first we would have 4 times 8 is 32, cancels against 2 as 16 in the denominator. Then we cancel pi in the denominator, and there is still pi remaining in the denominator. Then we have mu I squared a raised to the fourth power, and the denominator still misses a squared. Is that a surprise? Our result says that the result itself is independent of the radius of the conductor, because a, the radius, cancelled. So we began with the total energy and we obtained it as mu I squared over 16 pi. Now this is the total energy of the magnetic field that is caused by a current uniformly distributed in a conductor with circular cross-section and at 1 meter length. So this is the energy inside that conductor, the energy of magnetic field. Now, having that in mind, we can return to our energy definition of an inductor, which in fact said that for a linear inductor, the energy of magnetic field is 1/2 of the inductance times current squared. So we know that this is 1/2 inductance current squared, or we can say that the inductance is 2 times the energy divided by the square of the current. Okay, so we have this equation, we have the energy just here established, and we can therefore use the equation to establish the inductance, and that is the energy mu I, 2 times the energy mu I squared over 16 pi, and what remains? I squared. Good luck, we have not made a big mistake because the current cancels out. And the value of the total energy is mu, the total inductance is mu divided by 8 pi. Now, the most common case for conductors is copper, which is slightly diamagnetic, but very slightly. So we can count that the permeability of copper is similar to the permeability of vacuum. And vacuum permeability is 4 pi times 10 raised to minus 7 Henry per meter, where we can cancel 4 pi against 8 pi, and we would get 1/2 multiplied by 10 raised to minus 7 power Henry per meter. So if there is 1/2, that's 0.5 times raised to 10 to minus 7 power. So we would have 50 nanohenry as the result per meter. Just this could be quite a big value, which can turn, or which can score a big difference in the properties of a coaxial cable, for example, at low and high frequencies. So at this time we have no measure for whether an inductance is big or low, but we will return to this point when dealing with coaxial cable impedance, and we will find out that this could be important. Questions? So if I can summarize a little bit, we have distinguished between external and internal inductance of a conductor, the external being caused by magnetic field caused by the current within the conductor outside the conductor, and the internal inductance being caused by the current flowing through the conductor inside the conductor. Especially at DC, the second one might be important. We have found that calculating internal inductance is barely possible with static definition of the inductance, and we had to use energetic definition, which we found suitable for the calculation. We have calculated one simple case of a circular conductor and its inductance per meter. Now I will start with something that is a bit different and describes induction of a voltage into a conductor. There are two important laws that will guide us through that. The first of them states that you get an induced voltage if the magnetic flux through a loop changes. Now the induced voltage is established like this is called the induction law. So the voltage that is induced is directly proportional to the time derivative of the flux flowing through that loop. We can see this as an integral means to find out the voltage that is induced. It gives you a good value for the total induced voltage, but it gives you no clues on where it happens. It's just an integral law. At the same time, we have another law that we have already used, and this is the law, Lorentz equation, for the force that affects a charge with an electric and magnetic field. That is, the force is equivalent to the charge multiplied by electric field strength, which is the part of force caused by the electrostatic field, plus the vector product of velocity and magnetic flux density, which is the magnetic part of the force. Just repeating, this is something that can carry out work. This does not provide any work, although it might provide acceleration to the charge. Now those,
Sir,
yes?
could you please move the camera a little bit up, or the paper down? It's like we cannot see, or at least I cannot see what's written up. Yeah, now yeah.
Thank you very much.
Yes.
Thank you very much for this remark.
Thank you.
So again, we have got those two laws, and to make an illustration of how both of them work, let us examine a very simple cause. Let us have two massive rails that, for example, railway rails that are positioned in a parallel way. So we have two rails, and we will steal one pair of wheels from a wagon. That is something that is very robust. So we will have the pair of wheels that will be sitting perpendicularly on the rails, and this pair of rails is connected by a stick that is quite robust and metallic. So we have a very good electric connection of those both rails. And we will also have some magnetic flux density. Let's say it's a homogeneous flux density that flows in this direction into the board. So there is some flux density, magnetic flux density B. We have some distance, small d, of the rails. We do not insist to have the European or the, for example, Japanese or other distance, just there is some distance d. And now, to complete that, we would have a voltmeter connected to both of those rails. Now this is a closed loop. And as those rails are quite robust, metallic, we can neglect the resistance, at least at the beginning. Now, at the beginning, there is no movement. So, the voltmeter should show no voltage. There is no source that would cause electrons to move. Now, let's start moving. So, we will call somebody to just walk, possibly a soldier. He is used to walk in a manner that has constant speed for long. So he would work with dragging the stick along the rails with a constant speed v. Moving with a speed v means that with 1 second you just move by v meters in the direction of movement. So we can say, okay, in 1 second the stick would happen to move from here to here, which is just the velocity v. What happens now with the voltage? We can assess it twice. First, the simple way, mostly taught at secondary schools already. If you move the stick in this direction, then the loop, which is here, will be larger. In 1 second, it increases by this surface. And this surface is easily obtained by V times D. So this is an extra surface. But as we have constant magnetic flux density all over the experiment, that means that the flux flowing through the loop has increased. The flux has increased by VdB. So the voltage, and let's forget about the orientation at the moment, the voltage magnitude would be BVD. That is the reply, the kind of information that we can obtain out of the induction law. But we do not know how that happened. Was the voltage induced into this rail, or was it induced into this short piece of rail that happened to be in the loop? Was it induced to the voltmeter, or was it induced to the stick? There is no clue for that within the integral law. It just says that the total voltage over the whole loop is equivalent to the time derivative of the flux. That's it. So we know now that there is a voltage, but more or less we can't very much see inside the problem what happens. So let's try to examine the other equation. Now, if the stick, which is a metallic stick, moves along those two rails, then it means that the whole stick moves within the magnetic field. Now the stick the conductive stick consists of two quite different parts. One is the part that is directly and very firmly sticked to the material, that is atom nuclei and some of the electrons that can move to the conduction belt. So those are moved along and they cannot move. There is nothing that happens to them. But a conductor, that's a media where there are electrons that are quite free to move once there is an electric field. Well, so far we have no field, so we start to move the stick, and an electron with a charge is moving against the magnetic field flux lines. And we can easily see that there would be a force that affects the electron. Well, okay, there will be a force. So what would be the direction of that force? We have a magnetic field flowing this way. We have a stick that carries the electron in that way. So we have a V times B, which tells us that the result of the force goes upstairs. But the electron is a negative charge. So finally the electron would be dragged downstairs to the lower end of the stick. And as those electrons in conductive belt are able to move, they would start to move, and they will move down the stick. But as soon as those electrons are moving, something strange happens. They are leaving that part with positive charge upstairs. So we would have positive charge upstairs, plus, and a negative charge downstairs. But that's not the whole process. The most tricky and nice thing of the universe is equilibrium. Once those electrons would move down, there would be a negative charge and a positive charge upstairs. Those charges would create an electric field. And this field strength within the conductor would act against the movement of the electrons. It would drag them back to their nuclei. And this all would have an equilibrium where, well, the equilibrium would be raised if and only if the force that is caused by movement in the magnetic field would be equivalent to the force that is caused by those charges dragging them back. What would be the electric? So we would have to understand that at any time there must be an equilibrium, which would tell us that the E and V times B are equivalent. Just they have the same size but different direction. So we can tell that the equilibrium states that E is V times B. I have omitted the vector product because in our experiment everything is perpendicular, so we can only work with the magnitudes. So once E is V times B, we have an equilibrium. An equilibrium in which the lower part of the stick is negative and the upper part of the stick is positive. And if we can or want to express that in a voltage, then it's quite simple. If there is a homogeneous electric field with a strength E over a length D, the total voltage would be E times D. So it follows that E times D is the voltage. So we will have a voltage that would be E times D, which is VBD. Well, and you can easily check that we have obtained the same amount of voltage caused by moving that conductor within magnetic field. Just now we can attribute this more specifically. We now know that in our experiment the total voltage over the loop is B by D, where B is the flux density of the magnetic field, V is the velocity of motion of the conductive stick, and D is the distance, the length of the stick. So both laws gave us the same result, but we now know, using the Lorentz equation for force, that we only obtain induced voltage within the stick. The non-moving parts, like the voltmeter or those rails, do not affect it. In fact, the induced voltage would be there even if there are no rails. If I just carry a stick through a magnetic field, I would obtain an induced voltage on it. Just if I do not connect a voltmeter, I might possibly not see it. but the voltage will be there. It is a result of movement of a conductor through the magnetic field. And the word through the magnetic field is understood watching this part of expression. If the velocity is perpendicular to flux density, or we only take the perpendicular part, or we use a vector product of V times B. That is what matters as to induced voltage. So we have now found out the first part of the trick of induced voltages. We have a generator of electricity that works based on a conductor that moves with a magnetic field. This is an important point to understand, and I intentionally try to describe it using two different laws. But it's the same thing. It's the induction of voltage given by a change in magnetic field. Your questions, please. Well, there are no questions in the chat. I can't hear no questions. So I will continue. Okay. Well, we have so far seen a part of the process which is called induction, inducing a voltage into a stick or into a conductor. Now, what if we have the person which is just pushing the stick along the rails, and well, what about automation? What about replacing that person by the electromagnetic forces itself? So what about switching from an electric dynamo to an electromotor? How to do that? Well, we will again have those two rails. We have some sponsor that gives us strong homogeneous magnetic field still, and we want to replace the walking person for his tiring work by an electric source. So instead of the voltmeter, we connect a source. We connect a voltage V. Well, at this point we have to make a little bit addition to the circuit. There is no source with zero internal resistance, and at the same time those two rails, despite of being massive, do have some resistance. Also, the resistance on the crossing from the rails to the wheels would be very small, but not zero. So let's put there a resistor, and this resistor connects to the circuit. So now at any time we have a loop again. There is a source of voltage and a resistor, and one rail stick the other rail. We have a loop, and nothing moves by the moment when I switch on the voltage. What happens then? Well, we have a circuit that has some resistance, and when I switch the voltage on, there would happen some current, which will be given by voltage divided by resistance. So there will be a current, and that current would flow around the loop. Now, it is important to study the behavior of the stick connecting those two wheels. The rest of the setup is very tightly screwed. If you have examined a railway, that's something that is very, very tightly screwed to the bottom. So the rails could not move. The source also should be done in a way that it cannot move, but this stick and the pair of wheels could move. So what happens within the stick? We have there a number of electrons that are running against the current sense. So we have there a number of electrons that are just moving in this direction. Again, those electrons are moving perpendicularly to magnetic flux density, which is present there. And those electrons, when moving, would be subject to a force. And negative charge, direction of movement of electrons, magnetic flux density direction, those electrons will be affected by a force that goes that way. Now those electrons would try to concentrate at one end of the stick, which would leave a positive charge. So we have the stick, and the electrons are somehow concentrated here. So we have positive charges here. And those two charges attract. So what we observe is that the whole stick is affected by a force in that direction. Although the force originally has affected the electrons, the attractive forces between electrons and the nuclei would result in a stick forced to move that way. And if the force is enough to overcome friction, the wheels and the stick would start to move in that direction. To find out the force, we would have to again calculate the force at here. So if there is a current, that means that we have a transport of charge. And therefore, we would be able to find out that the force affecting the stick would be B I D. Well, where B is the magnetic flux density, I is the current flowing through the stick, and D is the length of the stick. Okay, so we have a force that forces the stick to move, and the stick starts to move and moves faster and faster because there is an acceleration. So according to Newton's law, there is a change in the speed and it moves faster and faster. And now let's say that we have an infinite railway. We have a very strong sponsor that could grant us and grants us a constant magnetic flux density over the whole infinite railway. We have everything prepared so that there are no losses, and whenever the stick is on the railway anywhere, it has the same feeding. So we have an ideal condition, and we neglect the losses by friction at the air or the surface of those two rails. Now, I would like to ask you a question. Would the stick accelerate forever? Or is there any limit for the speed of the stick? Your ideas? No ideas?
No, for now.
Okay, so I have first limit that should be obeyed at any time. It cannot be faster than light. The velocity of light is a limiting velocity that cannot be overcome. So far we can't find out how. Why? Well, okay, you can say, okay, the stick would become infinitely massive due to the theory of relativity and therefore it would not accelerate. Right, but there is another limit. And now this is very important to understanding of all electromotors or electrical motors that are in operation do have somewhere this limit, which I should tell you. Well, we have a stick, and by imposing an electric voltage on it we get a current, and due to the current we have a movement of charges, and due to that we have the stick forced to move to my right hand side, and it starts to accelerate and it moves. But the arrangement is still same as before. Once the stick starts to move, we have a conductor moving within a magnetic field. And as we remember, we have an induced voltage into the stick. Now the voltage is plus here, the source has also plus here, so in fact those two voltages do subtract, and as the voltage induced in the stick increases, the force driving current through the stick decreases, and there is a speed, a limiting speed, at which the voltage induced into the stick would be the same as the voltage of the source. At that moment, the current would vanish and there will be no more force to speed up the stick. Let us find what speed this is. So at we have the voltage that is induced here, and if this voltage is equivalent to the voltage of the source, we just can keep the letters, we would have an equilibrium. So at a speed of v, which is now I will make a big V to see that this is voltage and this is speed, which is the voltage divided by the flux density and the length of the stick. At this speed, we would have the induced voltage in the stick of the same size but opposite direction than the feeding voltage. It will neglect its effect in the stick and we will have no more acceleration. Just you might think that this is something funny. Well, for example, another example of this arrangement is a motor that tracks, for example, Prague underground cars. Just we have no sponsor, so that we have to make the magnetic field somehow by a coil inside the motor, and one stick would be a pure use of that costly obtained magnetic field. So we use a loop, a coil that has many turns, and each side of the turns acts as a stick, but the principle is the same. And now, just for example, within Prague underground metro, with the feeding voltage of 600 volts at least, it depends on the distance from the changing station, but that might be up to 900 volts of the feeding voltage. And at this point you have the voltage induced into the motors at some 25 kilometers per hour, equivalent to the voltage that is in the feeding line. Then there are some tricks that I use to speed it even more, so that the car is not limited to 25 kilometers per hour. But the important point is that the induced voltage is something important. It is present in any kind of electric drive, and you have to count with it in the construction. But for us, the important point is that we have established that there is some final velocity at which the stick will not be accelerating anymore. But now, well, okay, let's stay with the stick. Let's say that I have a strong sponsor that gives me 2 Teslas of magnetic field. The stick starts to move, I have some current. At some velocity the stick is no more accelerating. Are there any ways how to achieve more acceleration at this moment? Your ideas? Well, I have 2 choices. I can increase the feeding voltage. If I increase the voltage, it will overcome the so far induced voltage in the stick, and the stick will accelerate to a new velocity at which the induced voltage would be equivalent to the voltage fed to the rails. So that's the first possibility. There is also a second possibility. If the friction is sufficiently low, that is something like the motor is not fully loaded, then I can decrease, or I can ask the sponsor to decrease magnetic field. If the magnetic field decreases, the force would decrease. In most motors that would mean the momentum, the torque momentum of the motor would decrease. But if it's not loaded rather much, it would work anyway, and therefore as the induced voltage decreases, it would be possible to increase the velocity. This is the trick that is done in traction cars like trams and underground, that you control not only the voltage feeding the winding, but also the voltage that creates the magnetic field. And if the motor is not overloaded, if you are not running uphill, you can decrease the magnetic field in order to decrease induced voltage, in order to increase the maximum speed. So now this is an important example that more or less tells us the principle of electric dynamo or electric generator, and at the same time it gives us an insight into the function of an electromotor. It's quite an important topic. Last chance for questions. I have promised to make 2 small breaks, 5 minutes, within a lecture. So this is a good time for another break. After 5 minutes, I will again ask you for questions. And if there are no questions, we will continue. Still no questions? Well, okay. I think that we have made a big job today. We still have some time. And I promised you a puzzle. So I'd come with one. The first of you who will make a correct solution, I mean full solution with equations that prove the solution, will again qualify for a gift. And if we meet one day, I hope so, you will be able to get some wine. But anyway, the puzzle is quite interesting. And our physics relies on one important point, and that's the equivalence of what different observers would see. I mean, let us see two wires that are charged so that there is some voltage between them. Let's say it's a two-wire transmission line. So we have that line. There are two lines, two wires, one and second. They are parallel. And because there is voltage in between those two wires, there is some, for example, positive charge here and some negative charge density here on the other line. And an observer, just watching the lines from here, would see that there is static, non-moving charge, and this charge gives rise to electric field strength, electric potential, and electric flux density. And that's fine. That's a situation we have already investigated. Good field would be obtained by superposition of the fields of those two individual charges, and it works. But now, what if we have another observer, and this observer is moving? For simplicity, he would just move in the direction of the transmission line. So we have observer 1, which is fixed, and observer 2, and he moves along the line. What the difference is? Well, first, the observer 2 does not see charge densities that do not move. What he would see is moving charges. So this observer would see a pair of currents. For him, there would be a negative current here and a positive current here because those charges would move, or vice versa. If he moves, he would see this current down and this current up. And therefore, he must sense a magnetic field. Because there are two currents, and we have already established the way how to find out a magnetic field of two currents. So a moving observer along those two lines would have experienced two fields. He would still have two charge densities sitting at those wires, and we know that there would be an attractive force between those two charges, but as well he would see two currents of opposite directions, and those two currents repel each other. Now, this is a violation. This is not good, because at this moment we have one observer who can observe those two wires as attracting each other at some force. And we have the other observer who observes two wires that are attracted at a different force. And possibly if the speed is big enough, there might be a big difference between those attractive forces in the wires. Well, fortunately there is some solution to that, so I will give you a hint. Once the observer moves, he will observe the same force, because once he moves, and now comes the tricky thing, if he moves, or if those two wires move against him, the theory of relativity gives us, or stipulates, that there is shorting distance according to the move. Yes, very slightly, you know, there is the square root of 1 minus v over c squared, where v is the velocity of the observer, c is the velocity of propagation of light in free space. And that's, for small velocities it's not much, but as he moves faster and faster, in fact, those two wires get compressed for this observer. And therefore, he not only senses magnetic field, which drags those two wires out, but as the same amount of charge sits on a shorter section of a conductor, this observer would get bigger charge density on those two wires, which then would happen to create stronger electric field and increase the attraction of those two wires. So now we have two wires that are attracting each other at higher value, and currents that are repelling them, and the resulting force per meter length would be the same for both observers, so that they would see the same universe, although one of them would sense electrostatic field only, while the other would have sensed a combination of electric and magnetic field. Now the question is not really very easy. It deserves a bottle of good wine, and what I ask you for is to prove that this holds. That is to find out the force that the observer, the moving observer, would attribute to magnetic field, and the force that the moving observer would attribute to electric field, and find out that the difference is the same like the electric field force for the non-moving observer. It's a kind of thinking. This is an extra puzzle. I am not going to examine this at examinations because we are not doing relativistic electrodynamics, but on the other hand, it's an interesting question, and it finds out that electric and magnetic field, after all, are only one force manifested in two different manners, and that the manifestation depends on the observer, on whether he moves or not. But after all, I will leave this to you as let's say a puzzle, or as some extra work that will guide you, and if you do it, you will really understand the forces between two conductors. Is the puzzle clear? I mean, not the solution, but the given. Let's, for simplicity, we will treat two conductors of negligible cross-section that are placed in vacuum, and the distance between those two conductors is much bigger than the cross-section or the diameter of the conductor, which is non-zero but small. So this is an extra work. Let us wait. Again, I am not going to describe that to full details at the consultation on Monday, but if there is no solution by Tuesday, by next Tuesday, then I will tell you. Ladies and gentlemen, we have used the whole time that has been assigned to our lecture. We just arrived to a point where we would talk about virtual work, so that's what we will start next lecture with. We will try to calculate a dragging force, an attractive force of an electromagnet, of a device that is used to attract metallic objects, and that is what we will do 1 week later at 8:30. Thank you for your presence here.
Excuse me.
Yes?
Last week I sent you an email about the textbook written by Iskander.
Yes. You are right. The textbook written by Iskander, well, I can borrow you my own piece because the Iskander textbook is not in the library. There is the book by wait. This the Hyatt Engineering Electromagnetics is available in the library.
Yes.
But unfortunately, at the moment, I'm not sure what works, because in fact the government has asked us to stay at home. So I don't know whether the library would work within next 2 weeks, even for myself. So what I can do is that I borrow somebody of you, my personal copy, which I will be able to do only when I go to Davidse. This will not be this week. I'm sorry.
It's fine. So, may I ask you, do you have an electronic copy for that? Whether you have it or not? So you
Well,
can
I think I could have an electronic copy in Davidse, which I will have to find out. Again, when I will be able to move to Davidse, I will walk there and do that. So it seems that it should happen by next Tuesday, unless I acquire coronavirus or some of my relatives. That would fix me at home for more time.
Okay, thank you.
Ladies and gentlemen, it's been a pleasure to lecture for you. I intend again to have a consulting hours on Monday evening if you wish to consult, and the lecture would be on Tuesday. That falls for the 3rd of November. And that's it. Bye.